Okay, polynomials. Let's start by defining what a polynomial looks like. It's an algebraic expression where you have a coefficient, I'll call that a to the n, times a variable, and I'll use the letter x to the power of n. So you might have something like 3x to the fifth. So this would be your a to the n, and this would be your n value. And then you add your next term. So I'll call that a to the n minus 1. That would be your next coefficient, so maybe 2. And then x to the n minus 1, which would be, say, x to the fourth. So n is 5, and now n is 5 minus 1, which is 4. And then this pattern continues. So you get a n minus 2, x to the n minus 2, that's the next term, and you would just keep doing this pattern until you get to your very last term, and your very last term won't actually have any x's in it. It'll just be something like plus 3 or minus 2 at the end, and so it'll just be a, and we'll call it 0. So n minus 1, n minus 2, n minus 3. In fact, you'll finally get to a point where you have a to the 0, which will just be a constant term. And there's a condition on this. This beginning term here will never be 0. Otherwise you wouldn't have any x to the n's. So that's one restriction. So that cannot equal to 0. And another restriction is that all those coefficients are real numbers. So you won't get any imaginary numbers, and the n values have to be whole numbers. So n belongs to the wholes, so you're only going to end up with, again, whole numbers are 0, 1, 2, 3, 4, and on. So you won't end up with any negatives or any decimals or fractions in there. So there's a number of restrictions that define what a polynomial is. There's also one other key term, which is a polynomial has a certain degree. So let's write that down. So a polynomial has degree n, and yes, that's the same n as this n value up here, and it will have that leading coefficient. The very first coefficient will be a to the n. And those two terms are going to be quite important. So notice we put this thing into degree order, so those x to the n's come before the x to the n minus 1's, and that will let us know the degree, which will later on let us know the shape, along with the leading coefficient will also let us know the shape of the graph. So here's a few examples just so we can get an idea of degree and leading coefficient and what some of these things are called. So for my first one, I'll just start off with a really basic graph. F of x is equal to 3. For some of these you may even know what these graphs look like, and let's try and fill this in. So the degree of this one, well, it's got x to the 0's in it. There's no variable part. It's all a constant, and the leading coefficient, we'll call that 3. So you kind of imagine an x to the 0 here, so that tells you the degree, and this tells you the leading coefficient. But we don't really need those. Anytime you see a constant term, it'll have degree 0, and the number itself will be your leading coefficient. And this is called a constant function. Let's take a look at another example. If you have g of x equals to 2x minus 1. Well, now the degree is 1, because there's a little 1 that gets written up here that we imagine. The leading coefficient is 2, because that's the number that comes in front of the degree 1 term. And this is known as a straight line, or a linear graph. Let's move on to another type of graph that I think that you've already seen. This is a degree 2 equation with a leading coefficient of just 1. That's the 1 that is here that we don't write. And last year, hopefully you learned that this is called a quadratic. I of x, the next example, will move up to x cubes plus some other stuff. Notice you don't really need to worry about the other stuff. All our answers are coming from the degree of the biggest term, which is usually written at the front. If it's in degree order, it's written at the front. So this is degree 3 with a leading coefficient of 6, and this is called a cubic function. J of x, we'll move it up one more, so minus 4x squared minus 4x to the fourth. Now this isn't in degree order, so you do need to realize that this is the largest degree, and so really this should have been written minus 4x to the fourth minus 4x squared. To save some time, I'll just say, well, this is actually a degree 4 equation. The coefficient, the leading coefficient, is minus 4, and it's this minus 4 that I'm using as the leading coefficient. And this is known as a quartic function, Q-U-A-R-T-I-C. And I think I can squeeze one more example in here, k of x, and I'll make it negative x to the 5 plus 3x squared minus 1. This is degree 5, and the leading coefficient's negative 1, and this is known as a quintic, Q-U-I-N-T-I-C, quintic function. Some non-examples, just so you can see what are not polynomials, are these sorts of things. Root x plus 1, because that's like x to the 1/2, and 1/2 is not a whole number, and this needs to be a whole number. This is known as a radical, and we'll be studying those a little bit later. Another example is 3 over x. That's because this can be written as 3x to the minus 1, and again, this isn't a whole number. That's because this type of function is known as a rational function, and we'll be taking a look at those later in the course. And of course, if you have something that looks like it's a degree 5, maybe this looks like it's a quintic, but it can't have anywhere in it a negative exponent, because that's not a whole number. This is still another type of rational number, and we'll be looking at these later in the unit. Okay, let's take a look at all the graphs of these things. The graphs of every single polynomial, and we'll call it f of x, they're always continuous. And what that means is there's no breaks in them, and there's actually no sharp corners in them either. And what this really means is you can draw a polynomial function without lifting your pen from the paper, and generally they have nice smooth curves to them. So for example, if I just draw a function that looks like this, that's probably going to be a polynomial, because there's no jumps or gaps in it, and it's got some nice smooth curves to it. Of course, a linear function is also a polynomial. It's nice and smooth, it doesn't have any gaps, it doesn't have smooth curves to it, but it is a nice continuous function. Whereas some non-examples would be something like this, which you may have seen last year as an absolute value graph. That's not a polynomial. Or if you had something that went along and then maybe jumped like this. So if there's a gap, if you try and draw this and then you have to lift your pen to get to this point here and continue it, then this is a gap, and so this is not a polynomial function either. Even though this part might be smooth over here, the entire function is not a polynomial function. Okay, let's take a look at how the degree and the leading coefficient affects what the graphs look like, and we're going to make a fairly big table or chart for this, and it'll be helpful to know this graph, so spend a little time making sure you really know the shapes, and it'll help you for the rest of this unit. So to build this, we're going to take a look at what's the degree, and we'll start off with easier ones and move to harder ones, and we'll also talk about whether or not the leading coefficient is positive or negative. So if it's positive, we'll put it into one column, and if it's negative, we'll put it into another column, and we'll draw some pictures in there, but I also want to talk about what the domain of these graphs look like and what the range of these graphs look like. So we've got leading coefficients could be positive or negative. We'll talk about the domain and range and the degree. So let's start off with a simple one, which is this degree 0 or constant graph. If you have a constant graph with a positive number, it looks like a flat line. If you have a constant graph with a negative number, it also looks like a flat line. The domain is x can be any number at all. And the range is y is just going to be one single value. So I'll just use a little, maybe I won't use a double line, it looks like an equal sign, just a single line like this. So like for the positive leading coefficient, y is going to be positive 3. For negative, it's going to be negative some number, and the range will just be that number. You can't go any higher or any lower if you have a flat line. For a degree 1 equation, we have a positive leading coefficient. So this is a graph like y equals, we used to call it mx plus b. If this leading coefficient, if this m is positive, it goes up. If the leading coefficient is negative, it's a graph that is a straight line and goes down. And the domain of all of these are all real numbers, and the range are all real numbers because it goes up and down forever. Last year you took a look at degree 2's, which are quadratics. So if you have ax squared plus bx plus c, and really this is like a, and this is really like, this is a2, a1, and a0. That's our new kind of notation for it. If you have this sort of graph and the leading coefficient, your a value is positive, it makes a u-shape going up. And if you have it negative, it makes a u-shape going down. The domain continues to be xer, but now y values are either greater than or equal to something, or y values are less than or equal to some number. It depends if you're talking about a positive leading coefficient or a negative leading coefficient. If we go on to a degree 3 equation, and this is where it gets a bit new for you, this is the shape of a degree 3 equation. And if it's a negative leading coefficient, this is the shape of a degree 3 equation. It's xer and yer. Let's move on to degree 4 equations. A degree 4 equation has this shape if the leading coefficient is positive, and it has this shape if the leading coefficient is negative. Again, x can be any number at all, and the y values are going to have a minimum or a maximum. So the y's are either going to be greater than or equal to something, or the y's are going to be less than or equal to something. If I go to a degree 5 equation, a degree 5 equation looks like this, or it looks like this. Again, x can be any real number, and the y values can also be any real number. Now this pattern actually continues past this. You can have degree 6 and degree 7 and degree 8 equations, and we're going to look at some of the patterns within these patterns. So I've actually done some of these in green and some of them in blue, and maybe you can actually see some patterns with domain and range and what the shape of these things look like throughout these and as they would continue into the future. For instance, one pattern you might see is that x's are always real values, and another pattern you might see in blue, y's are always real. And so if the degree is odd, if the degree is 1, 3, 5, and it skips, it keeps going. So if the degree is odd, then you'll get yer. If the degree isn't odd, then y is of single value, or y is greater than or less than. In fact, past the degree 0 one, which is kind of boring, it's always greater than or less than. So there's another pattern in there. So if the degree is even, then it's y is greater than or equal to something, or y is less than or equal to something. You have to know what the leading coefficient is.